As you said, I'm Patric, Lawrence Berkeley National Lab. I'm a software engineer in Christine Pearson's group. We run the materials project. My background is in high-energy nuclear physics, so I'm somewhere in between science and engineering. The materials project is I should stay close to the microphone. The materials project has now over 30,000 users, and we're trying to disseminate properties and calculate properties from first principle calculations and disseminate that to the public and to those 30,000 users. We keep adding properties and we keep adding materials. We're right now at about 70,000 materials, unique materials, right? Each of those materials might be based on many structures, and we do that comparison and that organization into materials that are unique in their definition. Our homepage is at materialsproject.org, and we have all our code on GitHub. In general, the paradigm shift that happened was basically from an Edisonian approach to an in silico approach. And before, in the lab, material scientists would basically go try and error, that's the Edisonian approach, and think of a structure, make it in the lab, mix something up, try to make it automatable, not try to make it in more mass, and then learn that, well, if they apply it, it actually doesn't work, so they throw it away again. And you do that a few times until you're lucky and you happen to have the one that you wanted. The in silico approach in material science, at least, and when the materials project started now, is that we run all those possible structures through our machinery and calculate their properties from first principles. It might be vast calculations for those who know, and you throw up a big bunch of things that don't fit your application and the requirements of your application, and then the one or a handful or maybe up to 100 that come out of those millions of calculations are the ones that we would forward to a experimental material scientist, and then he could try to actually synthesize them and that way make that whole materials design process faster, less expensive, and more predictable. And that has been the idea behind the Materials Genome Initiative that started 2011. Materials Project is a key player in that initiative. And the database statistics in the upper left corner, you see we're about 70,000 inorganic compounds that we have on the site. We also have, out of those 70,000 compounds, 53,000 have band structures. We have a big, you can see that right here. We have a large set of elastic tensors that has been up to until we started calculating them. There have been the hundreds in the literature or less. So that's a order of magnitude more in those expensive calculations that are important for many applications. And we have data on electrodes and also on nanoporous materials and on molecules. So this whole database is a database of inorganic crystalline material structures and their properties. And if you go on materialsproject.org, first thing you'll see is a periodic table where you can actually select chemical systems and search for specific elements. You can narrow down that search with filters that we have, and you end up with a list of materials that fit that criteria. And each of those materials will have a landing page, what we call a materials details page, that lists all the details of our calculations and the properties that we've calculated. And that data you can also access interactively through for instance, here in a Python notebook through our REST API, and that interface basically lets you access programmatically all the data that we have. It's publicly disseminated, so anything that we calculate and is on the page will be accessible to the materials science community. Here's an example for the materials details page that you'll get for one. This is titanium oxide for a specific titanium oxide, sorry, for a specific MPID. And you'll get the exact structure that we've calculated and relaxed. Its general properties, and that detail page actually scrolls down for quite a while that you can actually have a more detailed look at the electronic structure, the band structure, X-ray diffraction patterns, wolf shapes. We also added elastic, piezo, and dielectric properties. And very important, that page also keeps track of the provenance. That means what calculations did we apply, what steps did we do to arrive at those structural properties, and then also who maybe submitted that structure, who came up with it, which paper did we find that structure in. Okay. And you might have noticed maybe that each of our materials, each of our 70,000 materials now also has DOIs. And I talked about this at last year's SciPy. That's the project MPCite, where we're basically trying to solve the problem of citing our materials data. The problem that we always have is that papers would basically query the crystalline structures from materials project and then cite, here's 2425, it's just our materialsproject.org and then a generic paper that come up. And same here is another example where they looked at for all compounds that have 100 atoms and a unit cell present in the materials project database. But the actual question is, which ones are those? And can we make that reproducible? And DOIs come in very handy because our materials are a good match for those DOIs. And in our definition, a material is a set of similar inorganic crystal structures. And those materials on our page stay unique and are also stable and defined. So how does that in the end look? We've had examples now already where a user would get that DOI from a landing page on our website and then cite it in their paper, which then directly would link back to that detail page. That's all been done. We are becoming, since we had 70,000 of those entries at OSTI, which is the client that issues those DOIs, we became their star data client. And the next step we're working on right now is to start collecting those DOIs as into a data collection of DOIs so that users could cite those 3,052 oxides maybe as a list to a link and embed it in their paper. Next, a general overview of how we produce our data, the internal steps that we take. We started originally with crystal structure databases like the ICSD and used the structures that are in there to generate a submissions database, so that is basically keeps track of all the structures that run through our machinery. Those submissions would be converted automatically and their structural definitions into workflows. Those workflows are predefined what calculations need to be run, and they use PyMagin to do materials analysis and materials input-output to VASP files, etc. And the workflows also use Custodian, which would take care of the error recovery during VASP calculations. So for instance, if a VASP job fails with a very known error, the Custodian has recipes to fix that error and resubmit the job. Fileworks is our workflow manager that basically takes care of those about 10 steps that each structural calculations right now has, and each of those calculations depend on the previous calculation to finish. And Firework would send this to our supercomputing resources. All of this is set up pretty agnostic with respect to the supercomputing resource. And after the calculation is done, we parse the output directory using PyMaginDB into what we call tasks. So each calculation has VASP directories output, and we compile those tasks to get all the information that we need out of those VASP calculations. And we have the final step before it actually goes into the web application, and the materials API is a compilation of all those tasks into a set of materials. And that's where the circle then closes, because users could now use those materials on the website to actually make new materials, do substitutions on materials, and resubmit it into our workflow using, for instance, the MPComplete service that would allow them to initiate calculations and add materials to our structure, to our database. A brief mention of MongoDB. We use it, as you saw in that previous picture. All those gray cylinders are databases, and all of our steps talk to a Mongo database, and we use it for everything. So the workflow engine uses it, our web service and our web page talks to a Mongo database, our applications for specific materials applications are talking to a Mongo database, and also our calculations, keeping track of each of our process in our high throughput calculations is done using a Mongo database. And the main advantage that I want to mention here, it's simple, but for us it's been very important, is that MongoDB originally, when we started this and still now, has dynamic documents and doesn't need a schema. So it's very, very scientific developer friendly. So it's like people that are coming from a scientific background, since Python, since the data model is basically the same as a Python dictionary, and it's basically the same as a web standard JSON. They all map very straightforward to each other. It's easy to understand for somebody that is a postdoc in computational material science and also wants to develop code that would fit into that machinery. And over the time, that has been proven very, very powerful in terms of making use of that human capital. There's been a disadvantage, which was that data validation originally was not in MongoDB, so something like energy above the Hall equals blueberry would be fine, but that's actually now also available in Mongo database, and we also on top of this have data validation scripts that do that on a nightly basis and check our output. How do we create workflows in that big scheme? The software that's involved with workflow generation is called Fireworks. That's a generic workflow manager. And we've recently developed a package that's called Automate, which is specific to materials science workflows. So Automate has simple code that would allow you with like 3 lines to set up a structural relaxation, elastic tensor calculations, dielectric or piezoelectric calculations for the properties, phonon, Raman spectroscopy, X-ray absorption, molecular dynamics, surface science. So there's a growing list of workflows that are available in Automate and easy to set up and then deploy to a cluster to run that calculation. So what Automate would specifically do is take an input structure with some optional input of what my VAS parameters, for instance, are, what the VAS command on that specific cluster is, and then do some pre-processing with PyMagen in terms of checking that structure and generating VASP input directories and so on, and then would set up first an optimized structure run. When that finished, we would do a static calculations to get, for instance, band structures out of it, where one of those boxes, one of those fireworks, actually does write a VASP input into the output directory, applies parameters that would make those calculations run more efficiently or more successfully, run VASP with custodian, as I said, to keep track of errors, and then store it in a database, as I've shown before. So this happens for all the workflows that you see happening here. Another effort that we're working on right now is MPContribs, which is a contribution framework that would allow users to contribute data and apps and structures back to the materials project and allow it to be disseminated through materials project. We've often gotten that request when people use materials project and as the user community grows, that they would need help sharing the data and the data that they've produced with the world, and that's usually not something that a scientific group has the manpower or the will for it. So we're working towards helping users attach data to our computationally produced data. So you remember there's a detailed page here, materials detail page, and the idea is that users like from the advanced light source at LBL is one use case. For instance, they measured X-ray absorption spectra to learn more about rare earth substitutes and permanent magnet properties. And what we would need to do in this case is basically set up that pipeline that takes data from the instruments, which is basically text files, CSV files, and then also integrate it with phase diagrams that come from materials project. So they're very interested. I have another slide for more detail in comparing their measurements on the fly while it's being produced with something that's in materials project already to give them feedback. And then the output of that data would then be attached to structures in a materials project as a simple entry in a detail page, and then also with a landing page to the specific data set. That's the goal. We do the same for theoretical data, for instance, the diffusion coefficients that are based on a VAS, but that we don't calculate ourselves. So other users have calculated that, and we feed that data back in a materials project. MPContribs tries to solve that and many more contributors' use cases to get data on materials project. For instance, the workflow at ALS that I've been talking about specifically would take data from the beamline. What it outputs is a simple text file. That's how their instruments take their data and store it. There's a pre-processing reduction software called SciChem at ALS that would take those spectra. A user can subtract, do normalizations, generate XMCD spectra, and the output quantities that come out of it after that pre-processing step is something that would go into MPContribs and the steps that were taken to arrive at that output data set, at which point we can combine it and pull from materials project with phase diagrams that we've calculated. And we could marry that experimental data like it's shown on the lower right here. For instance, the green part is experimental XMCD signal, the total magnetic moment, And they've measured all these compositions in that iron, cobalt, vanadium space. The lines are and the dots are compounds that we have on Matthias project, and the phase transitions and the experimental data can be compared basically on the fly, and also disseminated that same way to users for phase diagrams. So, and what somebody taking that measurement would then look at is do any of my measurements actually coincide, or any of those magnetic moments coincide with phase diagram with phase transition that Matthias project knows. And we close that circle by using MPContribs and its capabilities to disseminate that to the public. Okay, so the last thing I want to show, and a little live demo of it, is contributing structures, data, and apps to Matthias project using MPContribs. What would happen first is that the structures that are missing in Matthias project would be submitted to MPComplete, which is the service that lets users suggest new structures to Matthias project, and we run that as part of our production and keep track of provenance and so on. Then we would link the data output to the MPContribs ingestion mechanism. There's various sources where that data could exist on the user's end. And through Jupyter Hub and a specific instance for Matthias project, we make it possible that the data can be manipulated from their own sources to prepare a contribution to Matthias project. Then there's generic explorers and the possibility to design custom landing pages for that specific data set. One requirement has always been by a user that, well, I contributed data to Matthias project, and it'd be nice if I could just get a link to my own landing page, simple but own landing page to cite in my paper. And we've had cases like that where authors are citing their own data and future updates with that landing page. And then, of course, in the end, MPContribs provides all means to actually interact with the data after the fact, get it out of the Matthias project databases. As an example for the first step, before I show a little demo, depending on how much time I've left, the MPComplete submission is basically either through our toolkit app on Matthias project or through a Jupyter notebook. In this case, it's 77 structures that were not existing in Matthias project. The user puts them in, and we calculated them all successfully. You can see that 77 workflows actually make about like 1,000 calculations already that we have to run. And it ends up on the Matthias project. This is part of the detail page for this material, again, with a DOI automatically, since the user contributed it to Matthias project, and it also says who submitted it and what possible papers, like BibTeX citation and so on, it's all included here. So the provenance, even if it's submitted and suggested by somebody else, is kept track of. And the next step would then be MPContribs, which is integrated with Jupyter Hub, with a Jupyter Hub instance, for the reason that we just want to circumvent any installation necessary. So the idea is, you want to start contributing, just go here and start playing. And the Jupyter Hub is run with Docker containers, so each user that signs into our Jupyter Hub gets his own container. Even if you upload data, it's sort of in that gray area between, it's still in your own container. You can destroy it, you can remove it anytime, nobody else can access it. But we don't have to install software or you don't have to install software just to keep your data, your high-level data, private. So this is sort of an intermediate solution that makes it a lot easier to run that involved set of services that MPContribs has without the user needing to set up database interaction and all of that. The example that I have here is from Slack. They have data on MOSE2, pretty simple experimental data. And what we've gotten, or what he has on his basically hard drive, is a zip file of text files that is really small, and the user would go to jupyterhub.matthiasproject.org, upload this, and would also start a pull request, a use case to what a submodule to MPContribs, which is MPContribs users, which has like small code snippets that let him extract data from wherever source he uses. So let me show this from there in the hope that this presentation works. So where I'm at right now is actually jupyter.matthiasproject.org. You can see this is my GitHub nickname here, and I'm in my own container. Everyone gets so this looks very private to a user. The file that's for MOSE2 is in here, and we could now go to the ingester. I call it the ingester app, but basically what this pull request started is a Slack-specific small pre-submission processing that the user can load that also loads like some standard metadata that comes with it, and that's very important, where the user can actually decide, okay, now I'm going to change the author, the reference, somebody who has submitted data in this use case before has actually a template that he could manipulate. And the way then this data gets processed and the zip file gets processed, you can see that by selecting this project, it automatically loads a pre-submission from that submodule users and Slack use case. And this is just, what you see here is just a Jupyter notebook cell. So this is actually editable. So if the user decided to have some extra flags in here, you could actually go in and add this to manipulate the pre-processing. And you couldn't run that in the background. It would actually get data out of the zip file, add spectra, and add tabular data. And on the fly, you could now look at what this would look like in Materials project. So this happens still all within Jupyter Hub, and it's basically a dry run of what that system or that contribution would look like. And you can see here that each contribution has very simple components. It's hierarchical data. That's the stuff that you saw in terms of authors. Where is the zip file? And then it can be used for input parameters if necessary, maybe a formula. And then it has automatically extracted data tables. And for each of those data tables, I'm switching them off, a interactive graph is generated. And that's experimental data. So basically all that went in here is a glorified CSV file, if you wish, right? Internally, it uses RTML as a format container, but in the end, it's CSV plus some extra metadata and an MP ID to assign it to a specific material. So we can iterate this and say, like, we're happy with this. So what I'm going to do now is actually put this online. And there's two ways now that the user would first do. If a landing page for it would not exist yet, he would basically put this into the database that is running within his container. That's what I call a local test site. There is a local materials project bare bone website running within the container automatically. And he could add that data to the local test site or to materials project. For instance, the local test site that runs in MPContribs in the Jupyter Hub has the same services that the main page has too. So this can all be tried out before anything ever goes public. And all the use cases have an entry here. For instance, here I've actually put this in my local container before, and you should recognize those graphs from just now. And all this landing pages does is basically getting that contribution and then showing it in the way that a user would want those plots to be shown. So this is all, a user can all manipulate the code, simple Django templates on the front end. So even if I've done this with an undergrad who didn't know Python and who didn't know any Django, with a few explanations and based on templates, it's actually easily modifiable. Since this representation as a landing page for a data set is only something that the domain expert can truly know best. And so what I'll do now is I'll go on the main site, and then I'm about to be finished. So this materials project.mpcontribs. Oops, sorry. Why are you? It's a bit cut off here. Let's pull this over. There's a Slack MOSE2 landing page, which doesn't have any data in it yet because the paper is not officially published, but I'll still put it in. I'll get my API key from the main page, and then I'll just let it run, and you'll see that it tries to connect to Materials project, and I already have 119 contributions in there. It asks me whether I'm registered. That's how we prevent that other people just keep putting stuff in by sort of a trusted contributor scheme, which basically allows me to add contributors once they've shown that they can preview, once they can use the system and are trusted. And then online now, there's a specific identifier for this contribution. There's code with it on that data page, and all the tables and the graphs. And if I reload this, you'll see that data. That'll be it. Thank you very much.